Hi students, I wanted to help you visualize a complex problem in physics or any branch of science, engineering too. It's in particular the black body radiation, or you can think of solar radiation. This black core, as you can see, that is black body radiation curve, especially given by Max Planck, and well known as Planck's distribution function as well. It's not exactly the Planck's distribution function, it's actually solar spectral irradiance right now, but you can think they are very close. Right, so what I'm doing here is I'm using IPython notebook for visualizing this problem, and as you will see, I will try to regenerate this black body radiation curve, and we will try to play around with a parameter like temperature I have fixed here, but you can play with wavelength if you want. Alright, so let's start. The first step I'm taking here is, let's start with this equation. See, this complex equation, a function of wavelength and temperature. If you want to visualize this function, as a function of temperature or wavelength, it's actually hard, right? Because it's complex, not mathematically complex, not real or imaginary part, of course, but it is hard to make sense of the dependence of this function as a function of temperature or wavelength in our head. So in that regard, Python helps very well in visualizing this problem, and in particular I'm doing this IPyWizards thing, and you can see I've imported constants, these physical constants. This is the same complex function, irradiance function, Planck's distribution function, and these are the commands for plotting accordingly. The interesting thing here I introduced here in IPython widget is you can actually interact with your function with the introduction of one of your, or if you want, both of the parameters, but here I have fixed for temperature. You can make these buttons interactive buttons, sliders, right? So here it is for temperature, T for temperature, and you see here we get dot float slider and minimum to maximum and with step 50, and this function is telling what function to interact with and what is the variable that you want to interact with. So in this case, my function is the Planck's radiation function, Planck's distribution function like we saw earlier, and this T is the temperature, and that T, those values are here. You can actually slide and interact with the function, and you see here this is the plot right for this 500 degrees, and if I increase the temperature, I expect this graph tend toward what we saw in the beginning for the black body radiation, right? So let's increase the temperature, and what happens, let's see. I'm increasing the temperature slowly. It takes some time to update, but I already saw that this peak is moving or already moved toward the left, and it already looks very familiar, at least in terms of how it is skewed to the left. So basically, at that high temperature, which is close to solar temperature, you can interact like this, right? So again, if you decrease the temperature like this, it should go back to the flat line, right? And in the meantime, you are seeing this number change also. The irradiance at different temperatures should be different, right? Because the Planck's distribution function all itself is a function of temperature, and the voltage per meter squared should be different. Now you see this 12 here, it's already changed, right? So yeah, it's very good way to visualize any complex kind of functions. See it flattens out like that at low temperatures. Yes. All right. Okay, so that was the visualization, and with the help of this function, actually what you can do is you can estimate the surface temperature of sun because of this fact, Wien's displacement law. In other words, the product of the wavelength at which the black body absorbs the maximum, right, that wavelength times the temperature of the black body that is emitting the radiation is always a constant, and that is known as Wien's displacement law. So because this right hand side is always a constant, if you know one of these parameters, then you can estimate the other rest, right? So from the spectrum, it's easy to pick the wavelength at which the irradiance is the maximum at, you know, that particular temperature which we do not know, right? So looking into the spectrum, we can estimate that solar radiance irradiance peaks around 500 nanometer. That means in SI units, 500 times 10 to the minus 9 times temperature is the same constant, right? And this actually turns out to be 5800 for temperature, and that corresponds to very, you know, well reported value in literature for solar temperature. So that's interesting, right? So with the use of those IPython widgets, you can visualize any function. So that's all for now. Thank you so much. Bye.